its own probability, this mechanism. Is it true that the probability of picking x3 is actually f of x3? F of x3 is right here, right? This quantity from here to here, right, is how much the cumulative distribution been increased with that value. So this in here is actually f to x3. This in here is who? F of x1. And this in here is f of xk. So is it true that the chance of picking x3 by this mechanism, is it exactly f of x3?
Yes.
It's true because this is uniform in 0, 1.
Yeah.
And the chunks are f of x1, f of x2, f of x3. The smaller chunks have a smaller chance to be hit by my r. The bigger chunks, if something is bigger, has a bigger chance to be picked by that, right? R was uniform, so it has exactly this probability to hit kind of reverse or inverse x3, right? Okay. So now, in practice, I need to find one. How do I determine which x do I need? I need to find some x value such that f of xk minus 1 is smaller than r. It's smaller than f, the cumulative, this is the PDF, f of xk. Right? If r hits between, this is the f of x1, this is f of x2, this in here is big f of x3, because it's cumulative, all three of them. So I need to find the k minus 1 and k between the two f's, right? Two consecutive f's. So if this is the case, I'm going to return which one as my sampling value? X. So if, for example, r is between 0 and f of x1, where is that? That's in here, right? X1. So I'll return f1, x1. How many people with me? This is secondary grade math. There's no difficulty in here. And an algorithm, how do I find which k to return? Like literally, I have these f values, cumulative density. It's a discrete, so there's only like a bunch of them, say 100. And I have an r. How do I find which xk should I return? What's the algorithm that I'm going to use? Binary search, because those things are monotonically increasing. Binary search will find me the value in log k time, right? So binary search. Good. So that's the basic sampling from a non-uniform distribution. Suppose I want to do this for a continuous distribution. I want to replicate the process here, but for a continuous. So I have now f defined on a continuous range. Say, for example, 0 to 20. That's my sampling range. And with values in, this is a density function, so it has to be between 0 and 1, right? So it's the same thing, just instead of discrete, it's continuous. I don't have k values now, I have an entire range. Instead of saying sum of f equal 1, I say what? Integral of f of x dx equal 1, right? From 0 to 20. That's corresponding to saying the sum, now it's an integral. Who's going to be the big F of sum? This is also defined on the same range. The cumulative, this is a CDF. That's a PDF. So how do I define F? F was the partial sum up to some value. Partial integral. F of x is the integral from like 0 to x f of t dt. Partial integral. Again, I have a hard time with integrals. I think I said this before. I was not very good at them. So in probabilities, I always think of integrals as sums. Now, I want to do the same here. So this is also monotonically increasing, right? Because the integral adds up stuff that's positive. F being positive, the more I integrate, the more positive stuff I add. How do I do this? I get R equal rand, right? Just like before. And now, here's my range from 0 to max. Or what did I say? That's 20, right? That's my range. I'm going to plot the CDF like in here. So the CDF will look like what? Has to increase all the time. All the way to maximum value has to be 1, right? CDF, like in the previous case, goes to 1. So now, how can I, if R fits in here, R is still 0 to 1, generated uniformly, right? Uniform. How do I get a value in here if I want to do the same? I have to see where this intersects the plot and get in here, right? So this technically is F at -1 of R, right? Is the inverse of the F. This way, if this is X, this is who? F of X, the big F, the cumulative. But the other way, if this is R, this is F of -1 of R. So applying the same idea, I need to be able to inverse the cumulative. So this simply requires binary search, and it works for any small f, any big F. As soon as somebody gives me the F values, no matter how weird they look like, if I get, this is a fixed support, say 200 students. If I figure out the sampling property for each one of them, I can compute the big F, and then I can do binary search. I don't need a particular property. In here, I need something. Need to compute or estimate or something F at -1 of R. I need to find a way to handle that. So I can't do it for an arbitrary small f, which means an arbitrary big F. I need to find a way to do the inverse. Now, some functions have known cumulative densities for which I can compute the inverse analytically, right? Analytically, as in I get a formula. Some functions are too hard to do analytically, but we have all kinds of numerical optimization and numerical estimation methods, right? Even though I don't have F-1 formula, I could use some numerical approximation to get it. That's good too. But some functions are just impossible. We don't know how to compute that big F inverse. So then this method wouldn't work if I don't have a way to do that. Right? Now, if I do have a way to compute big F, I could just still replicate some binary search, right? I could try a value. Now, see how R relates to, I tried this X, right? Again, I can compute F of X, but not the inverse. So I can say, okay, how does F of X compare to my R? It's too big. It means what? Move to the left side. Now try another X, is that too small? And eventually, with kind of like binary search, I get pretty close to that exact thing, right? So I'll say, or some sort of binary search. I put quotes here because this is continuous, using F of X. Right. I could apply any approximation that gives me this. This has a name. This is called inverse transform sampling. Not a very good technique. This is the most easier to understand because it comes very naturally from this one here. It's a very, very direct generalization of a discrete to continuous, but it's not something that leads to interesting sampling algorithms. this particular way of thinking about it. In here, it's a Wikipedia document. There is a proof, which I don't want to do. No, the proof is on the other one. There is a proof that this could be done in a slightly more general sense. But again, I think it's not very interesting. I think it's okay for you to know, okay, I can take this method and apply it in a continuous space. But it's not very interesting to developing fancy sampling algorithms. Like all the Gibbs sampling, and in particular, the one that's being used, I think is called Metropolis algorithm for sampling. That's a lot used in data, are not based on this idea, are based on a different idea. That is rejection sampling. You're gonna need this, I think, for your homework. Which we already talked about. Now for the homework, you can implement whatever you want. So as long as you get reasonable samples that match the generating distribution, you can do a little histogram. Once you generate your samples to see that you're matching the generative Gaussian or 2D Gaussian, you can plot this as a histogram versus the actual distributions and see that visually there's a match there. You don't need to compute any chi-square or sampling metrics, but you need to show histogram. Here's my original distribution, and here's my samples. They should kind of match. Rejection sampling means I have an F over some space. That's a PDF. And I'm gonna draw that space here. So what I mean by space is that if this is unidimensional, that's the real axis, univariate Gaussian. But this could be a three-dimensional Gaussian. But this might be x1, x2, and x3 if my variable is three things. Right? And this is the PDF. So that's F, the PDF. PDF is the density that says if this is a particular x1, x2, x3, that is the density in that point, right? This is F of x1, x2, x3. In a Gaussian, right, for example, you can say if I get a point x equal, I don't know, 0 point or something, 2.2. I can compute a normal distribution. If F is normal, normal has parameters like mu and sigma, right? Then I can compute f of x. Sometimes people write it f of x given mu and sigma. I don't like this notation in general, unless mu and sigma are some parameters or variables that need to change later on. Like a lot of algorithms that there's an E step that changes the parameters or something, then I put mu and sigma. But if mu and sigma are fixed in stone things that will never change, I prefer not to put them. I like to have variables when I write, only the variables that actually can change. If something is globally fixed, like mu and sigma are input to my program, I can't change them, I prefer not to write them that way. So then, how do you call the normal, right? What's the normal formula? Actually, I don't remember it very well. So what is it? 2, 5, sigma, right? What else? E
minus x
square divide by sigma square, like that? Maybe something, right? This doesn't quite work if sigma is 2 or 3 dimensional. Like you can't really, what is this, right? So it works in unidimensional case. In multidimensional case, there's a different formula for multidimensional case, right? If x is 2 variables, then you gotta do some vector things in here. We talked about that before at mixtures, right? So that's what I mean here. F is that kind of function. So how rejection sampling works? Sampling. sample some x in the x space uniform by components. That means if the x space dimensionality say is 3D, then what that means, I sample uniform and independent x1, x2, and x3. So if I need to sample for a three Gaussian distribution 3D, I sample independently and uniformly x1, x2, and x3. That is, I call my function rand 3 times. Then I sample y equal rand a 4th time. So this is called rand 3 times. Then I make one more call, also uniformly independent of the other calls y. And now the rejection sample says what? If this value y, so this is imagining that I pick a point uniformly on the space. I ignore the distribution. I just pick a point uniformly in the 2D or 3D space, whatever it is that the sample is, right? And then I pick a point, so I have this point, and I pick a point, I'm going to think of this y in here. What do? If y is bigger than f of x1, x2, x3, then reject. If y is smaller than f1, x2, x3, then accept the sample. I think we talked about this a few weeks ago, right? So this point here will have what probability to be accepted, assuming it's sampled enough time, or points around it are sampled enough time. It's going to be roughly df, because if every time y hits in here, it's going to be accepted. But every time y hits above it, it's going to be rejected. So the chance of including a sample like this would be roughly f of x1, x2, x3. Rejection sampling. This is a more interesting mechanism. Based on this, people have developed all the fancy algorithms like the Metropolis Hastings algorithm, which is a generalization of Gibbs.
Under the sampling is the same thing.
What?
Under x actually, under sampling.
Under here?
No, above.
Here?
Yeah.
Dimensionality. This is, for example, dimensionality is 3D. I sample 3 things, and then I sample a 4th one for the y range. So I think a 2D Gaussian sampling can implement it quite easily based on this idea. Sample 2, x1, x2, then sample a 3rd one, and then check how is the sample corresponding to f of x1, x2, for example.
So is x original 5 dimension?
x1, x2, x3 come from the space that the distribution is defined for. So if I have a Gaussian, that'll be an infinite range, right? Gaussians the support is minus infinity to plus infinity. Yeah. So I have to truncate that range somehow, because I can't really sample from minus infinity to plus infinity. What would be a reasonable way to truncate the Gaussian? If I say, okay, the theoretical range is from minus infinity to plus infinity, this is the mean, right? I say, okay, I can't really sample from a uniform theoretical range of plus infinity, minus infinity, so I want to truncate it here and here. How do I determine where to put those truncations? I want to go so many standard deviations from the mean, right? So how many standard deviations should I go by? How much is, how much mass, probability mass, is in 2 standard deviations? By the 3 standard deviation, 95, 96, something like that. So what if I do 4 standard deviations? Standard deviation is sigma, right? Small sigma, not a sigma squared, that is variance, right? So say I do 4 standard deviation, that should be like 99%. So I'm cutting off the tails, which are 1%. I should acknowledge that for whoever I'm writing this report and I'm doing this problem, say be careful, I cut off the 1% on the sides. Most people say fine, 1%, you know, but if you're Google or somebody big like Facebook, you don't want to cut 1%. Maybe you want to cut 0.01%. That just means more standard deviations, right? So you should know when you make something like that, you should acknowledge it and be explicit about it, so that whoever reads it doesn't pass through and have no clue what you did, and then leaves you the impression that you could have sampled a much wider range. Okay. So it's true that we have to truncate this, but we'll truncate it to something that's practical. So that's recapping the simple stuff. There is one more exercise that you guys have that is simple if somebody explains it, but otherwise could be a little tricky. I think we did that. I'm gonna do it again here. And maybe be more like, if you guys have questions about it. So sampling ununiform, discrete, without replacement. The first one I put here, I just erased it, that I pick an R1 and then an R2 and R3 if I want 3 samples, sample size 3. That was with replacement or without replacement? That was with. That means every time I sample something, if you look at your picture that was erased here, the next time when I call an R, I could have sampled the same object because I didn't change the distribution at all. Now I'm saying I want to sample without replacement. This is a hard problem. There is no easy way to sample without replacement and target the initial distribution. So my distribution here is the same, f of xi with sum of f of xi equal 1. And I would like, at the end of my sample, the end goal is the probability of any xi being in the sample. So I have a size here, sample size equal, say, k. That's not k, say t. That's given. So somebody tells me I need a sample of 20 students out of 300. So I have the 300, I have the probabilities over 300, and I know I need to pick exactly 20. Now I would like the probability of the sample to be as close as possible to f of xi. That's my end goal. But this is an ill-defined notion. Because if I sample 20 things out of 300, what happens to the total probability mass of the sample? Take this to an extreme. Suppose I sample 290 out of 300. Can I still match those probabilities? I'm asking a little subtle question here, right? So I have 300 things, 300 numbers. They sum to 1. And I say I want a sample of size 290 according to this distribution. So ideally, I'm saying as a specification, the probability of somebody being sampled overall, whatever the mechanism was, at the very end, the probability of being, this is called an inclusion probability. That is post-sampling. This is not the probability used by the sampling mechanism. This is after it's all done. What was the overall chance of him being sampled? That could have been 100%. Maybe my algorithm somehow, whatever it does, it picks him with probability 100%, right? Or 0 if I don't consider some people at all, right? Those will have 0 chance of being in. So I would like this to match that, but can I do that if the sample size is really 290 out of 300? Can I match those probabilities? What happens if I want a sample size of 300 out of 300 without replacement? Probability of everyone to be included in the sample is 1, right? So what happens if I ask for 299 out of 300? Probability will not be 1, but can I really match those probabilities? The real probability P of xi in the sample, if I sum all this over the xi's that are actually sampled. So I look at the ones I sampled, right? The 20 students or 290 students, and I sum not the original probabilities f of x, but the actual inclusion probabilities. What was your chance to be in? How much this sum should be? Has to be by theoretical statistics. No. That college level class probabilities that we took 4 years ago, huh? If my sample is of size 20, the sample size it can be seen as an expected value. Right? If I tell you I sampled 20 things, oh thanks. This cannot be 1, independent of the sample size, right? Think about it this way. If I tell you I sample 1 item, let's do over all xi. If the sample size is 1, and I pick 1 item, everyone had exactly probability f of xy. For sample size 1, I could match those exact probabilities, right? So I pick someone, say I pick him, but it doesn't matter who I pick. The sum of everyone sampling probabilities is 1. Now suppose I want to sample 2 objects. The sum of inclusion probabilities for everybody has to sum to 2. If my sample size is 2, the sum of everyone probabilities to be included must be 2. Otherwise, the sample size cannot be 2. If the sample size is 300, all of them, what is everyone's probability to be included? 1. The sum of everyone probability to be included must be 300, the sample size. What if I have a sample size of 150? Everyone's inclusion probability summed up must be 150. So this must be roughly the sample size. You can prove this much more formally with the expectation formula. But this tells me that this is not that possible. If the probability samples have to sum up to the sample size, that's much bigger than the sum of f's. Sum of f's is 1. So people will be like, okay, well, can I multiply f with the sample size? If I need to sample 20, this sums to 20, scale those f's by 20, and then everyone inclusion probability will be 20 each sample probability. Would that work? So again, I need 20 students out of 300. I started with everyone has some probability, f's, and I say, since I know my sum of inclusion probabilities will roughly sum to 20 at the end, I'll make every one probability be 20 times its sampling probability, the f that was given to me. Would that be reasonable? Would that be reasonable to say, okay, then probability of everyone in the sample, the inclusion probabilities, I want to be roughly the sample size that's given to me, t, times f of xi. Because the sum of f of xi sums to 1 times t, it will sum to t. What's the problem with this idea? I mean, the mathematics checks out the sum, but there is a fundamental probability problem with it. Can I take my f's, multiply with 20, and say I want those to be my inclusion probabilities? When is that not possible?
If I have a greater than 1?
That's discrete all the time, yes. Multiplying by 20 might be bigger than 1, right? If somebody had the probability of sample, say, 10%, I can multiply with 20 and say this person has now probably 200% to be in, right? That's not what sampling without replacement means, that some person will be picked 100% of the time, or even twice, as in duplicated to 100%. So doesn't work. So I don't want to dwell further into why this is a difficult problem, but you can play with it without mathematics, and figure out why it's so difficult, even with a die that has discrete probabilities on 6 faces. If I say sample without replacement, which by the way is not what the dice are used for, dice and coins are always with replacement. Every time I roll the die, I still have 6 possibilities, right? You can see how hard it is to start matching some initial probability, even proportionally, it's hard. So there's 2 ideas. One is approximate. F of x. The other one is approximate sample size. So I won't talk about this, but the second one is quite practical to say, look, I can't really give you t things, but I'm going to come up with a mechanism that makes sense and I can control it and I can produce proper inclusion probabilities, but I can't guarantee the sample size will be exactly t. So when people do polling for an election, they say I can afford to do roughly 3,000 phone calls, right? I can call 3,000 people. They start with that as a target, but they don't mind if they call 3,100 people or 2,900 people, right? When they say I need to call about 3,000 people to do my poll, they don't mean exactly 3,000. So if that's the case, then I can approximate the sample size. It's a mechanism for that. But if I want exactly a sample size, like your problem says, in your problem it says there, implement discrete ununiform sampling without replacement, you gotta get exactly t items. And the biggest requirement is, in all such problems, produce p of xi in the sample exact. So this might be an approximation to my given distribution. May not be exactly f of what I wanted, but this has to be calculated super exact. So my mechanism for sampling, even though the inclusion probability that I end up with is not directly proportional with f, it's an approximation, all that's happening after the sampling, say I do this election poll and I want to know what chance some candidate has to win the election, relies in calculating very exact the inclusion probability. What was the chance overall for an item to be selected? So in either schema, it's essential to have to be able to compute this super exact, even though it's not what the target says it should be. Because the estimator functions have a way to compensate for not having exactly the right probability. You know, it turns out that even if I want to sample with a certain weight in Massachusetts versus California versus Texas, even if I don't have that exact inclusion probabilities, my estimator for who's going to win the election, it's still accurate. There's a lot of mathematics in what I just said. The entire sampling books written on the subject. You need to take a course just in sampling techniques to do that. But it's not essential to match the given distribution. What's essential is to know at the very end of the sampling mechanism what was the chance that this item was included. So we ask you to implement such a technique, right? A particular one. The book that I showed you online has 50 techniques for doing this. This is a hard problem, so statisticians have thought about it for a long, long time. And my understanding of statistics in terms of like professional understanding is pretty weak. So the only books I can read are the ones from before 1980s. That's why the book I pointed out, it's written before 1980s. After 1980s, statistics got way too complicated, okay? So I'm just kidding. But I show you a book that's readable, okay, without having to go to get a degree in mathematics first. So I found that quite readable. It has 50 techniques for doing this, and I'm asking you to implement one of them. Here's that one that says, here's my f of x. It's not continuous because this is a discrete problem, right? So this is n, the population size. N is population. Very typical term for statistics, population, or the support. And let's assume n is about 1,000 for this example. And I also have the sample size. Say that is 20. It's given that I want to sample 20 items. Right? So the first step, I think some of you already do this problem. The first step is to, after sorting the probabilities, is to bucket it into size 20 buckets. So I'm going to group the first 20 items, the highest ones, and then the lowest, the next 20, and then the next 20. All of them will have a decreasing f, right? And the last 20. And how many buckets do I have here? N by 20 buckets. And now in each bucket, I take those probabilities that each bucket has 20 probabilities. I take them and I make them uniform in the bucket. So instead of having them from some top to bottom, I make them flat. I average all the probabilities in here, sum them up and divide by 20. And I do the same here, I'm gonna get a lower average, right? Why? Because the probabilities in here are lower than the ones in here. And if I keep doing this, I get a lower bucket, lower bucket, lower bucket, up to the lowest bucket, right? So now I have n by 20 buckets, and I change the probabilities, right? This is not my original f's, but they're pretty close, right? In each bucket, if you think about what's the difference between, say, some probability in that bucket and the new probability that's been averaged out. That difference is not that big inside the bucket, right? Assuming this f doesn't have sudden huge drops, so it's like a nice smooth function over 1,000 things. Each probability inside the bucket is pretty close to the average. Some of them are supposed to be actually higher, and some of them are actually lower. But I think the difference it's likely to be small if the bucket is small. If really this is 1,000 things and each bucket is only size 20, inside each bucket the probability won't vary that much. Okay? What's the next step? Sample buckets with replacement. So how many times I do it? 20 times. based on bucket probability. The bucket probability is what? So my object sample here in step 3 are not the items, are the buckets themselves. I know how to do sampling with replacement. That was the first thing I did here, right? I picked that R and I got my object out with binary search or whatever. But what's the sampling probability for a bucket? It's this thing, right? This value here. This is the sum of the probabilities inside the bucket. And now, is it true that the sum of buckets probability sums to 1? Because it's the same sum as before, right? So sum of bucket is the sum of the items in the bucket, f of xi, right? So if a bucket contains 20 things, the probability of a bucket is the sum of those 20 probabilities. So can I sample with replacement the buckets 20 times? Well, with replacement means just repeat 20 times the same procedure. So I sample once, I pick a random uniform R, I do the binary search, I figure out is this bucket. Then repeat, maybe it's this bucket again. Then maybe it's this bucket. This bucket is more likely to be picked up. In fact, this bucket will be picked up a few times out of 20, right? So then that results in counts, right? This bucket 1, bucket 2, up to bucket, what did we say, n by t, right? Number of buckets. I'm going to have some sampling counts. Sampled counts. Say this is C1, C2, up to C n by t. That is how many times in this part each bucket got selected or picked. Right? Again, this could be 0 because a bucket might be never picked, or it could be 3 or 4 because a bucket can be picked 4 times. And then the last step is, this is step 3, this is step 2, step 1. Step 4 is sample uniformly without replacement items in bucket, say T, how many items I'm going to select? How many times the bucket got hit? So if this bucket here, the biggest bucket, gets selected 5 times, what does that mean? I'm going to pick randomly and uniformly 5 items in it. If this bucket got hit 0 times, do what? Skip. This bucket got hit 3 times, pick 3 items uniformly. Can I pick, how can I do this without replacement uniformly? How does one does this? What's the procedure to get randomly 3 things out of 20? Right, because this will be 20 items in the bucket, I will select 3 of them. How do you pick 3 things at random out of 20?
The distributions inside a bucket of probability is the same.
This is uniform.
Yes.
So I just need to pick 3 out of 20 with uniform chance.
So you can adjust the probabilities after picking it from, right? Because you know what the distribution for the remaining samples will be that distribution.
But the distribution doesn't matter. This is uniform sampling. So I'm ignoring the distribution here. I'm just saying I want 3 at random out of 20 in such a way that every one of these 20 items in that bucket has the same chance. What's an easy way to do this?
Shuffle and choose 5.
Shuffle them, put them in some random order, and pick the first 5 in that order, right? That implies that my shuffling has to be uniform. So let me make this note in here. How does one does this? 2 steps. Shuffle, or in mathematics we don't say shuffle, we say permutation. Permute items randomly. And then pick first how many I need, CT, in that random sequence. How does one shuffle things randomly? I give you an array of 20 values, shuffle it at random. How do you do that? There's a function shuffle, right? How does it do?
Maybe I'll generate 1 to 20 random numbers and replace the indices with them. Like
Generate, call my rand function 20 times, generate a random value for every item, good, and then what? Then what?
swap the indices.
No swap. I have for every item that I want to permute a random value.
The indices which it should go to.
Use the value as rank.
As?
Order.
Meaning, what do I do?
Sort.
Sort. Sort the items based on these random values that I just generated. So let's expand a little bit this point. This means two things. Associate a random value Ri for each item, and then sort items based on Ri values. That's how shuffling works. It generates a random value for each one of them independently, and then it says sort the numbers based on these values. That's a random shuffle. And it only takes n log n, because it only takes the sorting, assuming the random runs in constant time. Okay? So that is part of your homework that you need to implement, this method. So you will take as input a distribution over some items. You would sort it, because to make this look good, you have to sort it first. And then you would implement this technique. Now the shuffle function you can call. Like you call random, you can call shuffle, but then you'd have to do the bucketing management yourself.
When you do the shuffling, is that okay if each item get the same random number?
The same random number?
Yeah.
That's not going to happen. When you generate 20 random numbers, you're not going to get the same value twice. Pseudo-random generators will not return the same value. The chance of them returning the same value in a big amount of time, say in 3 days, it's 1 over some billions. So that's not going to happen. Try right now. Try call random 20 times and see if the values are the same. They're not going to be the same.
Yeah.
That's it. Rand function, it's 0, 1, right? So when I say generate a random value by calling rand, I mean a random pseudo-random number in range 0, 1. There's no chance in practice to call that 20 times and get the same value. But if you do, that means your two items going to be next to each other after the sort, which is still a valid permutation. Okay? Are we happy with sampling then? Because I think there were some questions, so I felt like we need to do a recap on what this is. Now, sampling is a big deal. It's a big deal in mathematics. It's a big deal in data science because two reasons. Three reasons. One is the people who really need to do sampling, not because the computation problems, like you do sampling because my computer is not big to do the whole data set. But people who do election polls, they call people, there'd be no point in calling 300 million people to ask them how they vote. That's not the purpose of a poll, right? Same thing like in census. If I run the census, I knock in everyone's door to ask, who are you and what you're doing, right? But if I want to estimate the size of a population without redoing the census, I can do it very fast by doing sampling. If I want to estimate how many defect products I have, I'm Toyota, and I'm really interested in estimating how many trucks of certain kind will have a problem. I could wait for those trucks to break down and count them, or I can do some estimation in advance via sampling. Okay? Sampling is a very useful practical tool. Also, some of the algorithms that we implement, like LDA, they must use sampling simply because the distributions they need to work with, it's infeasible. That joint distribution It's just not possible to work with, independent of the computer you have. Even if you have a big computer, that will still be impractical to use that joint distribution. Right. And so in data, sometimes sampling is the right thing to go. So this, I don't think for you guys as data scientists, it's critical to understand all the math behind. There's a lot of math, but it's critical to be able to use those techniques properly. Okay. That being said, I think we need to, I'm going to talk a little bit about something else, because we're done with sampling now. And I think you're going to have one more homework 6. And there might be a problem about this, but this topic, collaborative filtering, which I want to talk about now, we don't want to make a big deal because this topic, it's both easy and it's presented in several classes. AI class, I think, even machine learning class, information retrieval class, and some other classes talk about this. But I will tell you some stuff that other classes don't say. The reason this is an important topic is because it's a gold mine, right? Right now, like in industry. The easiest way to make money for big companies is with a better collaborative filtering technique. So collaborative filtering, also called recommendation systems. So the basic notion is that there is a gigantic matrix of users and items called the items V. And I'm sure you have seen this, so I won't insist on it. What is in here? User I with item J. What is this? Let's call it Rij. This is a R matrix. Collaborative filtering. What is Rij? If these are Netflix users and those are the movies, what is this? Rating, right? How much they like it, right? So rating of items by user Y. Let's assume the rating is something 1, 2, 3, 4, 5. This is typical. It's not always, so there's important cases where these ratings are not 1, 2, 3, 4, 5. But if I'm asking you to recall the last ratings people have asked you for, Airbnb, Apple, or Netflix, would be 5-star things, right? So they do 4.5 now. That's fine. But most big companies use a scaling from 0 to 5, right? Notably, information retrieval internally, Microsoft, when it asks their assessors, evaluate how good this document is for that query. They don't have the same 0, 1. They might have a 5-grade scale, but it's not like the scale you guys have when you rate a movie. So there are some important exceptions to this rule. But in practice, I think this is quite typical, 1, 2, 3, 4, 5. So the first observation is that this matrix is very, very dense or sparse? Sparse. How many movies did you watch? How many? Like in the last year? How many, honestly? If you watch movies 3 times a day, that's fine. Did you watch 1,000 movies? Even if you watch 1,000 movies, how many movies are there in Netflix? How many? Make a guess. How many movies or TV shows included Netflix has? I think more. I think it's like 300,000. So even if you watch 3 movies a day and you rate all 3, you're still not making a dent within Netflix collection to say I've rated a lot of movies, right? And if you just don't do just Netflix, you watch all movies that there might be 1 million, right? Easily. So then you can't do that. Not to mention, the biggest problem is people don't rate everything they see. Now, I think rating got more into the human nature because everybody's asking you to rate everything all the time, and people got used to them because ratings it helps the user. You don't see that on Netflix, but the rating helps you. You see it explicitly on Airbnb. People use Airbnb, right? So if you use Airbnb, you want to rate because you want to be rated. Because if you are rated, it's easier to book next time. In Netflix, how does the rating help you? If you rate, what do you get? Better recommendation, because you influence this matrix, and because of this matrix, Netflix might give you better things to look at. Is that really happening? Do you feel like Netflix gives you good recommendation for you? I'm asking, honest question. Is Netflix really produces good recommendations for you? Do you watch that tag of recommendations and you pick from there and say, this is crap, I'm gonna ignore it. Let me just look at the new releases and pick one from those new ones.
Mostly based on the genre.
You go by the genre?
The recommendations are mostly based on the genre. Many a times.
But do you, out of people who watch Netflix, do you go by recommendations or you go by your own search or criteria? Nobody goes by recommendations?
I go by recommendation. Sometimes if I see the artist, the actor that I like, because they show up normally in the recommendation.
So here's a problem with understanding how good recommendations are from a metric perspective. You could say, I don't like Netflix recommendations, as in I don't think they're that good for me. But you have to judge them within the scope of what's possible. Meaning, if you don't like anything on Netflix, right? Obviously, you're not gonna like what they recommend. But if you like some things on Netflix and they don't recommend it, then it's a case to say, okay, there was something I wanted to watch and these guys couldn't find it for me. So when you judge a recommendation, that also applies to Amazon. How many times Amazon sends you an email about a pajama or something, right? And you're like, okay, I don't want it, right? Often. How do we judge whether the recommendation was good? That's a very difficult problem for Amazon, because Amazon makes money and spends money, a lot of money, on those recommendations. Whether they are ads on the website or emails to your inbox, they spend a lot of money. They want to evaluate how good the recommendations are. Now, if you are not about to buy anything from Amazon, they don't really make a mistake. They recommended something, and you didn't buy anything, you didn't want anything, so there's nothing they could recommend. They took a chance, essentially blind. But if you were looking for something on Amazon, and they recommended the wrong item, that's a problem for them. Because you might buy it from somewhere else, or you might decide not to buy it, or you might just not know about it. So when you judge recommendation, which is a big area of research now, how to evaluate recommendations, you have to judge within the scope of what the user is likely or intending to do, right? Now this problem is easier for Toyota than for Amazon. Why? Toyota has how many items to recommend? 5, 6 cars, right? I mean, there's options, right? You can get it with the radio or with a fancy radio. But that's not how recommendations go, right? They only have to decide whether they recommend you a small car, like, I don't know, the RAV4, or a big truck, like a 4Runner, right? Or some pickup truck. But their problem is not the kind of problem Netflix and Amazon have when this number of items is gazillion things. Yes?
So you're saying when they are recommending this decision is not important, the recall is more important, so they can have that recall.
They have ways to measure this, and precision and recall are built in. So out of how many recommendations, there's two things that get measured. How many clicks I get. Clicks is you clicking on that email or on that ad. That's an intermediary notion of interesting. And how many buys I get. I really ended up buying the truck or the item. So they measure two things. When they send you a recommendation, clicks and buys, or serious, even if it's not buy, if somebody puts that item in the cart and changes their mind, that's still considered very close to buy thing, like a clear intention of spending money. Now, the buy to ad ratio is very large. They can afford to send 10,000 ads for one buy. But the clicks, they don't like it to be that large, right? They don't want to send 10,000 ads for one click. That means a lot of ads or emails, same thing, have been totally misplaced. If you click on 1 in 10,000 of their ads, means they don't target you properly. Okay, so the basic version of this is I have these ratings, they're very sparse. How do I do predictions, right? So the basic version is, basic version. User similarity. So raw UZ is the similarity between user. I want to compute the similarity between users. And what would I do with that similarity? So before I do that, so let me say I want the ratings to be, I want a mean for the user. Let's call this normalization. So I'm going to compute the mean of a user, which is sum of the ratings for that user divided by how many ratings there are. And I'm going to compute the variance for that user, which is sum over all the items on this R UI squared some estimation of variance. And I want to normalize the ratings. I'm going to put a bar because those are normalized now. So now I have 0 mean and 1 variance. That's necessary because some users have way more variance than other users and different mean. Maybe I'm a nice guy and I give high ratings to everybody and he is a terrible rater, so he rates everybody down to the floor. By doing this, I kind of calibrate the users. Everyone has the same variance and the same mean. Right? So they say this is normalization. Then assuming I have that similarity, here's how I'm going to make a prediction. That is, if you remember the weighted k nearest neighbor, it's going to go by that. So predict the rating of user on an item. It's going to be the sum. So I'm averaging the neighbors. So this is Z users. Those are the neighbors. I take the ratings of the neighbors on that item, normalize, and I multiply with how similar this user is to the current user. Right? And then to be a weighted average, I divide by the sum of the similarity. This is just a normalization. Right? So this is how KNN works. If you remember the weighted version that weights every neighbor differently, it says take the predictions from the neighbors, but weighted by how close the neighbors or how similar the neighbors are to the current point. That's what's happening here. This is simply makes the row UZs into a distribution. That's what it does, right? But this is the predicted rating normalized if I want the actual rating predict. How do I move this rating back from the normalized space into the original space? I have to take this prediction that I've just got here. I multiply it with, how do I reverse this formula here? Multiply with the row and then add the mean back. That's just reversing this formula. Because my prediction is going to be in a normalized space, and then I have to move it back to a rating equivalent.
Why is that required? Why can't we compare the normalized version of the two?
What?
Why do we have to necessarily take it back to the original space?
Sometimes, if you want to really predict 5-star systems, like if you want to say, we believe this movie is worth 3 stars for you, or 5 stars, you have to put it back into the original space, right? I agree, maybe you don't want it. Maybe you transform this value into a probability, and then just rank the movies based on that probability, present a rank list. Fine. The problem is, who is this, right? How do we get who's similar with who? This is a fundamental problem in collaborative filtering, figuring out that some user belongs to a certain category or is similar to these other users, right? The first things Amazon or Netflix will try to do in terms of any such system is to say, Virgil's a new user. What other users are like him? Based on what he bought, based on the music he listens, based on products he checked out or ads he clicked on, whatever. I want to know who is like him. Because collaborative filtering main idea is to say, I'm going to predict a preference for you, be a movie or a product, based on what other people like you bought or rented or watched. Right? That's the collaborative filtering idea. If I know that you are like these other guys, and all of them watch these new movies, Transformers 6, I don't know what the real number is, but the next one, right? Right? Then I'm going to say, you are like them, they all watch Transformers 6, they all like Transformers 6, I think you're going to like it too. But I'm not trying to figure out whether robots are exciting to your brain. That's not. Collaborative filtering is not trying to see if you really like robots and why you like robots. It's just saying, you are like these other guys and they all like Transformers for some reason, I don't know why, I think you're going to like it too. It works pretty good if you are very close to this group of people and if they all consistently like that item, book or movie or song or product or something. That's how reviews on Amazon work, right? How often do you look for products and you quickly look for the stars to see how many people rated this product and how many stars it has? Because if people liked it, assuming Amazon doesn't tweak the reviews, doesn't let them be to what they are, right? If many people like it, you see 3,000 people all saying 4.5 stars. You conclude, I'm not even going to read the description to this thing. Whatever the company is saying, it's probably good because everybody likes it, right? And I think people have learned to trust more their peers, especially in a Western society, aka United States and Europe. People have learned the last 10 years to trust more the peer reviews, what other people are saying, than what the companies or the sellers are saying. Sellers always say in the Western societies, this product is the best. It's the best you could buy, better than anything, right? And because they all say the same, people learn to ignore that, right? Okay, everybody says the same. I can't really make a decision based on what the seller tells me, right? When you see an advertisement for a movie, they always advertise you like the best movie ever made, right? But they learn how to trust their peers, which have not necessarily good informative opinions, but at least more honest. People who didn't like it, they probably didn't like it when they say they didn't like it. Right? For this reason, a lot of articles in politics typically, they have so-called the people who comment on the articles, which act like reviewers effectively, because they say, I think this is good, it's bad. But those are not really reviewers. They paid promoters that they act like honest opinions, but in fact they're not. They will always say what they're paid to say, right? So some systems like Amazon and IMDb and Netflix work really hard to separate promoters from honest reviewers, right? Because once promoters get in, it's a matter of money. Like you could say, okay, how much promoters can do if there's really so many millions of people rating those movies, and how many promoters can really influence that score? It's not that easy. It's about money. If a movie costs $1 billion to make, I can probably pay a lot of promoters to put their reviews, right? And early on too. So I think those companies have a problem to distinguish between honest reviews and promoters, but that's a separate discussion. So back to this, a typical basic version for UZ is, how would you do this? How can I do this based on that matrix? How do I know two people are similar? I want an English version first. They watch the same movies and their ratings align, similar. Big ratings correspond to big ratings, and small ratings to small ratings, right? So let's do something like 1 over movies rated in common, well, items, because I general. Sum over rating normalized of UI I common times RZI. So this is a dot product, right? It's a sum. It's very similar to the cosine. It's the cosine has some normalization functions, but I don't need them here if I already normalize the ratings. Right? Note that this could be maybe between, I don't know, say 1 and -1. So the similarity doesn't act only in the similarity sense, also acts in the anti-similarity sense. In here, if I have a user which is anti-similar to me, how his ratings contributes. If this user gives a high rating to a movie, it's gonna lower my prediction because its similarity is negative. Meaning, me and my mom, we are very anti-similar. We never could watch the same movie. So as soon as my mom says I don't like this movie, there's a chance I'm gonna like it, right? That's how this formula works in terms of anti-similarity. If the coefficient is 0, means what? Negative means anti-similar, positive means similar, and 0 means no relation, no information. So you can tell 0 will be when the dot product is 0 perpendicular, right? And in here, 0 means that rating doesn't matter for the prediction as a coefficient because it's multiplied with 0. So that's the basic collaborative filtering. I'm going to mention quickly one idea that people have. Actually, let me connect the projector and show you some stuff. This problem at this level, it's very simple presented and very, very straightforward to implement or to work with. This is not the industry problem. In reality, in industry, these problems are very difficult. There's a lot of complications to it. I'm going to mention 2 of them, but not how to solve them. I'm just going to mention the complications. One such first thing I want to mention here is like with a lot of the stuff we did over the term, whenever we had a matrix, people have thought about decomposing it. So this is a basic data mining textbook that I think I posted online as a book that you can read. By the way, let me make a comment about this book. I think this is a reasonable book to read for a person which is not a computer scientist. No, I want to read something in the train to figure out what people are doing. It's not technical enough, and it doesn't pose enough problems and solutions to be a good book to use. But if you are, say, an undergraduate in engineering and you just want to feel, okay, I want to know about data mining in general, what kind of techniques are being used, this might be an easy book to read. In my opinion, this is not a book to use properly in a course at this level. Okay, the notes that we had were far more technical than this book. But for collaborative filtering, we can try to factorize this matrix, just like we did with topic models, and before with PCA and all that, right? Every time there is a matrix, people have thought of, can you factorize it into users and items? The idea would be, like in PCA, that the number of columns here in the middle, which is the number of rows of the other matrix. So this, by the way, if you're Netflix, you have how many users? 70 million? How many items? 200,000, right? If I do something like this, there is a middle k, right, between those matrices. The number of columns here have to be equal to the number of rows there. What kind of k am I looking for if I'm Netflix? I'm talking about 70 million times k, that's the first matrix, and the second matrix is k times 200,000. What would be the point of that k? It's the same point like in topic modeling and in PCA.
Average number of movies.
What kind of k am I looking for? What?
People's property.
Right, so it's, what k do you expect to see there? It's like a million? 100,000? What kind of k? If I want to really do a factorization like this, what should I look for in that k? Guess a k that I might use for collaborative filtering if I'm Netflix. What's the value that I would use? 50 or 60 or 80, something like that. What is that 80?
Same number of movies between
Think of PCA or topic modeling. What's K?
the movies that count the most towards features.
Are properties that people represent movies internally, right? So people, when they judge movies, they don't think of more than 50 properties of the movie. It's about history, maybe. It has certain actors, it has naked girls, it has bombs, it has explosions, it's a new movie versus an old movie, it costs a lot of money, or whatever, right? When you think of a movie, you're not gonna think of all the attributes that movies have, right? You're gonna think of few things, concepts or properties that are important, and it turns out most people have kind of the same properties they think. Now, each property can have multiple values, right? So these hidden concepts or layers or topics, they could be different for different users, but they all look for the same 80 to 100 things. Now, technically, like before, K has to be at least the rank of the matrix. If I want to do this exact, K has to be at least the rank. Typically, the rank is much larger than 80. So then we use some optimization. We say, given that we want a certain K, like 100, what is the closest decomposition of that has the K that we want 100, that's as close as possible to the original matrix, right? So we try to optimize something. We say we don't do it exact. We impose the K to be 100. So a lot of the initial, as of now, 10 years ago, in industry models were based on these decompositions. If you remember the Netflix challenge problem, when they give $1 million for whoever improves their algorithm by 10%. A lot of those algorithms initially were based on factorization of the matrix, the training matrix that Netflix would give to the users. Now, if you want to know what really happens, the trick in real problems is to build a user profile. Is not just to build a user similarity, me versus him, but to actually build meaningful profiles. Those are trade secrets. So Netflix wouldn't sell the profile. They might sell to advertisers how their ads relates to your profile, but wouldn't sell your profile. So the real industry-based recommendation systems are looking at this guy, this Virgil, and says, okay, how do I build a profile? A profile might be related to the actors he likes, or the genres he likes, or some sort of music he likes. I have to extract those concepts from the content. Actors are easy because they're listed in the movie, right? So this is like if you watch a movie with Angelina Jolie and you give it a rating 4, that corresponds to some value in your profile. If you watch a movie, again, a different movie with, what's her name? Nicole Kidman, and you don't like it, now it doesn't mean you don't like Nicole Kidman necessarily, but that has an impact on across all the movies you watch with Nicole Kidman, how that influences. The hard part is to extract those hidden properties of movies that are not explicitly stated in the movie description, like the actors. How do I extract certain aspects from the movie? Sometimes I look at reviewers and I do some text modeling on the reviews to see out of all the reviews for a movie, what are the things that people are stated the most about this movie. Maybe it's a very dramatic movie. Maybe it has to do with Jewish history during World War II. This is similar to what Google builds, they call the knowledge graph. These knowledge graph items are not necessarily words or keywords or entities, but they sometimes are concepts that people are looking for. So this is a very simple slide, and it doesn't have those concepts, but that's how stuff currently works, based on user profiles. So if you have profiles, you can think of the users. You can think of, this is the ratings that stated M1 and 2, that's their ratings. And now here's the profile qualities. That could be actors, genres, whatever else it's in those movies, music or something, right? And then you can apply machine learning in a pretty forward way. Say, I'm gonna say learn something from here in a supervised way and apply the same thing here. As long as there's a consistency between the ratings. I have to be careful with sparsity. Not all machine learning will tolerate sparsity. But then I say, okay, I'm going to predict for every user based on some model I learned from the system. So this is kind of how it works. Profiles and machine learning. That's how it's being done. Now, a big deal for certain items turns out to be the date. Movies have that property. Even if you like Star Wars 20 years ago, if a movie kind of like Star Wars would come now with the technology from 20 years ago, you wouldn't like it. But songs don't have this property. Turn out, some people like the old music as well as they like the good, the new music. So for movies, it's well known that the date, it's a big deal for everybody. For music, it depends on the user. Some users always prefer the new music. Some users always prefer the old music, you know, so on and so forth. Done. I'm being kicked out.
老板现在生病吗？不知道，不知道，还没讲。照理讲他会来的啊。